Hello everyone, welcome to another exciting video on next race. I was waiting for a long time to say something about classifying graphitic structures based on the type of bonding present. So here we are. Today I will say something about the effects and application due to the presence of single, double and triple bonds on graphitic structures. They are mainly graphene and graphine. It was long ago in 1947 when Dr. Philip R. Wallace proposed the concept of two-dimensional carbon structure with a hexagonal lattice. It was only in 2004 graphene was discovered by Andrew Jain and Konstantin Novoselov, for which they received the Nobel Prize in Physics for this in 2010. The technique for synthesis of graphene was very simple. They took a hunk of graphite and used scotch tape to peel off the graphene layers. They analyzed what they had left and found out about graphene. Almost 2 decades have passed, but graphene is still a rising star in the field of material science. Various other derivative graphene-based structures like graphene oxide, reduced graphene oxide, graphene quantum dots are taking over various research works. Now coming to graphene, graphene is a two-dimensional allotrope of carbon consisting of a single layer of carbon atoms arranged in an hexagonal lattice. It is still now considered as one of the strongest material known to date. One of the general properties of graphene I would like to mention is its exceptional strength. Exhibits excellent electrical and thermal conductivity, making it highly desirable for electronic and energy applications. Graphene is transparent and highly flexible, and last but not the least, it is incredibly lightweight, making it useful in aerospace and lightweight structural materials. Due to such diversity in its properties, it has been used in various types of applications like electronics, energy storage, sensors, composite materials, water purification, and biomedical applications. One of the important current requirements is the scalable production of high-quality graphene, which still remains a challenge, but researchers are actively working on developing cost-effective methods. In organic chemistry, where we classify organic compounds based on the types of bonds present, here we can classify graphene, graphane and graphine. Likewise, in graphane, single bonds are present in structure, as you can see in the alongside picture. This was first established by the hydrogenation of graphene. Still, it is difficult to perform complete hydrogenation of the entire graphene sheets. For the sake of terminology, here I am referring to graphane as the material that corresponds to complete hydrogenation of graphene. The most common method proposed for preparing graphene is by hydrogenation of graphene. It involves exposing graphene to atomic hydrogen, which can lead to the addition of hydrogen atoms into the carbon lattice. This process aims to saturate all the carbon atoms with hydrogen, converting graphene into graphane. However, achieving complete and controlled hydrogenation of graphene remains a significant challenge. While we can't easily perform complete hydrogenation of graphene, doing incomplete hydrogenation affects this band gap, and we can also tune it to our desired requirements. This modification alters the properties of graphene significantly. Graphene is an insulator with a relatively large band gap, which means it does not conduct electricity well. The addition of hydrogen atoms also make graphene stable and less prone to oxidation compared to graphene. It has potential applications in the field of dry electrics, protective coatings, and also gas storage. For the example of gas storage, here I mean the hydrogen storage. Now coming to graphine, which is another form of carbon allotrope that can be thought of an extended version of graphene. It is composed of sp and sp2 hybridized carbon atoms arranged in a lattice structure. Graphine can exist in different forms, including alpha graphine, beta graphine, which have different arrangement of carbon atoms. Graphine has a higher degree of sp hybridization compared to graphene, giving it interesting electronic properties. It is predicted to process tunable bandgap, which could be useful in semiconductor applications. The synthesis of graphine is a very difficult task. If it's possible, I would like to discuss it in another video. The applications of graphine are quite similar to that of graphene, like electronics application, energy storage, catalysis, gas separation, filtration, etc. There is a lot of promise for graphene research in the future in many areas due to the outstanding qualities. Graphene has promise as a component for electronics and optoelectronics technologies of the future. Through development based on graphene, improvements in energy storage such as supercapacitors and batteries are anticipated. The aerospace and automotive sectors may undergo a revolution as a result of graphene's use as a reinforcement agent in composite materials. Because of its special properties and biocompatibility, graphene may be used for tissue engineering, biosensors, and drug delivery systems in biomedical industry. Solutions based on graphene are being investigated for use in environmental applications and production of renewable energy. These are some of the sources from which I have taken help. These works have been published in very reputed journal. You can go through them if you want to enhance your knowledge in the field of graphene. This video is nothing compared to the immense data that is currently available in the research world. Graphene and its derivative would surely be upscaled and used at large in future. If you want to know more, go to Google Scholar. I will soon bring new exciting content. Until then, stay tuned only on Next Race. Thank you everyone.